Hello, everyone. Welcome to our Lagoon Masterclass on Lagoon Recirculation, Benefits, Design, and Implementation. I was going to show my face here briefly at the beginning of this webinar. My name is Patrick Hill. I'm one of the founders here at Triple Point. I actually have done a lot of lagoon work myself. I've been in the field, done installations. This is me on a boat doing a sludge survey. As you can see there's quite a bit of sludge floating on the surface of this particular lagoon, but that's the nature of the beast when it comes to lagoons. And sometimes I like to get out of the office and out of my desk and actually get on a lagoon and see what things are like. So I hope I can provide some value here today and hope provide some good information. So today we're going to talk about we're going to do a brief intro into Triple Point, talk about why you might want to recirculate water within your lagoon system, some of the modeling around why it makes sense from a treatment perspective, some of the design aspects, and then look at a few case studies before we conclude. So this is part of our masterclass. So we've been kind of developing this masterclass concept, and we see it as having 6 main modules in it. And Lagoon Process being the first module, and I think we're getting close to the end of that. We did some webinars in the spring, and then my colleague Brady did a webinar last week, and I'm doing another webinar tomorrow. And so just do check those out. Eventually, we'll set up course tracks on our Lagoon University site so that you can kind of follow each different module separately and kind of go through, and eventually we'll have some kind of certification for being a lagoon master. So we've been working on this, and it's been really well received, and we're really excited to see how excited people are about it. So Triple Point. For those of you who don't know us, we focus, we're a company that helps lagoons get upgraded to meet stricter standards or to be more efficient or expand capacity. And we've been doing this for 16 years. We've done over 200 lagoon upgrades. And so we really like to think of ourselves as specialists in lagoons, in that we're specialists. We've developed this process for developing and delivering a lagoon project we call it our Lagoons Do It Better process. And it starts with diagnosing situation, gathering data, identifying core issues, defining objectives, and then goes into a design process where we really try to tailor our solution to your lagoon or to your system as the best we possibly can. And that really is an iterative process that incorporates talking to the end user, talking to the engineers, talking to everyone involved, and making sure that we design the very best possible system. And then finally, we help to support and follow through implementation, commissioning, and operation. And ultimately, we stand behind the system with our "we say it, we do it" guarantee. So at the end of the day, so what? Why is this important? Well, I think this is important because we have developed this proven process to be successful, so that every time we do a lagoon upgrade, we're delivering the right result for the customer. So it really takes away the risk because we've codified and developed this process, but also it ensures assuredness of success in the project. Whatever your objectives are, we're here to help you meet them, right? And so this is why we developed our Lagoon Do It Better process, and hope that explains a little bit about what we do and why we do it. So recirculation. So I always crack this joke. It's like we've all seen the pharmaceutical commercial where they're like, do you have problems with Lagoon DO, algae, effluent ammonia, effluent BOD, effluent TN, effluent concentration volatility? Well, you should talk to your doctor about lagoon recirculation, because lagoon recirculation is something that can help with all of these things. And I'll go through this in this presentation, but we first learned about lagoon recirculation from Steve Harris. And Steve is a consummate lagoon expert. We worked with him on co-hosting a bunch of training for lagoon operators in Missouri and Iowa and other parts of the country, and also doing webinars. And, you know, part of what he did was he was always hired by the EPA or state EPAs to come in and solve lagoon problems, right? This lagoon's not working, solve this problem. And a lot of times he would recommend recirculation. And it's actually not really a new concept. It's something that's actually been borrowed from activated sludge. Activated sludge has been doing recirculation for a really long time. And what it is simply is moving water from one part of the lagoon system to another part. So it might be the, you know, pulling out of the effluent pond and putting it into the primary pond would be a very common application. But really, you can put water anywhere you want in the system. And I'll explain why it helps. Some people get confused by this, you know, the circulation of water, and you know, we typically recommend about 1 times your average daily flow. So if your average daily flow is 100,000 gallons a day, we recommend recirculating 100,000 gallons a day to the front. And sometimes initially people look at this and they get confused and like, wow, that's a lot of flow. What happens to all this flow if we're sending 100% of what we bring into the plant to the front? Do we discharge? And I think what's important to know, and this is why it sort of sounds like circular logic or circular reasoning in a certain sense, it takes a minute to kind of get your head wrapped around it. And that might be true for, you know, where you're circulating water from the back to the first lagoon. And, you know, you might not discharge a little bit for a few hours while the whole system equalizes, but ultimately, the time that the water stays in your lagoon system, what we call hydraulic retention time, remains the same. And so this is the equation for hydraulic retention time. Very simple equation. It's the number of gallon per day flow you've got coming into your lagoon divided by the volume of the lagoon, right? And so with recirculation, if you look at this equation, you're not adding flow to the lagoon. Your ultimate, what's coming in from your collection system is remaining the same. The volume is not changing either. And so water does come in and flow back out. It just goes round in a circle one more time than it would have. So if you think about it in terms of a gallon of water coming in, if we could label that gallon of water coming in and we could watch it as it goes through the system, it would stay in the system for the same amount of time. It would just go around the circle twice. And so you know, at the end of the day, the equation stays exactly the same for recirculation. So it's pretty interesting. I think I've always gotten a little confused by it initially until I really started thinking about it, and I got back to this equation, and this made a lot of sense to me. I'm like, oh yeah, of course, we're not changing the hydraulic retention time. We're just moving the water around more. So why? So I'll go through various reasons of why. So first one is you can help to improve dissolved oxygen in different parts of your lagoon system by recirculating water. This graph here shows you the inverse relationship between BOD and DO. As your BOD decreases, your DO tends to increase, which makes sense because BOD is biochemical oxygen demand with an emphasis on oxygen. And so at the beginning of your influent, right, you've got a lot of this BOD in the water that's consuming oxygen. And as it moves through the system, that depletes the dissolved oxygen. And as it moves through and you get less and less BOD, the water is able to hold more oxygen. And so at the back of the plant, you just tend to have about 5 milligrams per liter or 6 milligrams per liter of oxygen. At the front of the plant, you tend to have a lot less. Sometimes you'll have 1 or under 1 milligram per liter of dissolved oxygen. And so if you need more DO at the front, then the pumping water from the back to the front helps to boost your oxygen levels in the first lagoon. Makes a lot of sense. The second reason you tend to get a lot more oxygen at the back is that you grow algae, typically at the back of your plant. Algae, like any plant, when sunlight is on it, it photosynthesizes and converts carbon dioxide to oxygen, and that turns up as DO in the water. And so that algae helps to boost oxygen at the back of the plant. Again, you can take that, move it to the front of the plant, give yourself a little oxygen boost. The third thing with BOD is BOD is broken down by a microbial community that develops, and that microbial community will grow more or less depending on how much food it has. Okay, so at the front of the lagoon in your influent cell, your cell 1, you tend to have a much more vibrant, diverse, and larger microbial community. Why? Because there is more food at the front of the lagoon system than at the back of the lagoon system where there is less food. So by taking that BOD from the back and transporting it to the front, to that first influent cell 1, you are more readily breaking it down because you're giving it to a microbial community that's hungry, that's got lots of, there's just a larger population, and it will break down. And so this is essentially why you typically see that a recirculating lagoon, a system that has recirculation in it, will get about 10 or 20% better BOD removal than a lagoon that doesn't have that. And that's why that when you see that you're struggling a little bit with meeting a BOD limit, recirculation could really, really help you. Not only are you going to deliver more DO, which helps the bugs be a bit happier on the front end of your lagoon, but you also are delivering the bugs more food at the same time. And so you tend to get better BOD removal. And it's really simply a matter of giving that BOD a second chance, a second bite at the apple to break down where there are bugs that will eat it at the front of the lagoon. So algae. With algae, you tend to grow it, as I mentioned in the previous slide, more towards the back of the plant. And what happens with it is that you end up getting thermal stratification across the lagoon. So, think of like you got the sunlight penetrating on the surface of it. The temperature is going to be a lot warmer of the water there. The temperature down below is going to be a lot colder. And so it's just like jumping into a lake. When you jump in the lake, the top layers are warmer, you're okay, you start diving down, wow, it gets really cold really fast. And so one of the reasons that algae likes to grow in the surface of the water is because the water is warmer and because it has access to sunlight as well. And so by recirculating water that has algae in it from the back to the front, you are helping to mix those layers of water, and you're helping to create some thermal equalization. So you're helping to make the water across the entire lagoon system be slightly colder than it would otherwise be, which then creates a less hospitable environment for the algae to grow. The second thing you're doing is you're moving the water a lot faster. And one of the things that algae likes is stagnant water. And so when you're able to move things faster, you're able to just create a less hospitable environment for algae to grow, right? It's moving faster, it's moving along, it's not as stagnant as it was before, and algae doesn't like that. Finally, and we'll talk more about this in the subsequent slides, by recirculating, if you get some denitrification, you're actually able to reduce the amount of total nitrogen in the system, nitrogen being one of the key food sources for algae. It's the things they consume when they're growing. And if you're able to reduce the amount of total nitrogen, you're able to reduce the food source, and you're also able to reduce the amount of algae. Now, caveats aside here, algae is a tough beast, okay? And if you have an algae problem, which a lot of lagoons do, no, every lagoon has algae, that's just a fact of life, but some lagoons have it to the extent to which they are struggling to meet BOD and TSS limits at the back. Recirculation is not a cure-all for that. It's not a slam dunk solution to your algae problem. It is a benefit, a partial benefit to reduce algae, but it may or may not solve your problem. There are other methods. We're going to have a whole webinar on algae coming up that will deal with how to mitigate an algae issue as it shows up. So I don't want to sit here and say this is going to solve your algae issue. It's not going to solve your algae issue per se, but it will certainly help a little bit. All right, so let's talk about how recirculation can help with reducing nitrogen levels in your lagoon system. And before we get into that and talk about some case studies around this, let's just do a quick chemistry lesson on what nitrogen is, okay? And there are different forms of nitrogen and that make up total nitrogen. So first you've got ammonia and ammonium, NH3 and NH4 respectively. These together are ammonium nitrogen. Then you have nitrite and nitrate, and finally organic nitrogen. All these things together make up total nitrogen. So think of it as adder. It's ammonia plus nitrite plus nitrate plus organic nitrogen. And we'll talk about nitrification, but in the next slide. But what you do when you nitrify is you convert the ammonia into nitrate. And so you're really not removing the total nitrogen. You're just converting one form of a nitrogen to another form of nitrogen. Now, the different things you hear and see about nitrogen, you hear the term TKN or total kilojoule nitrogen. This is simply the combination between ammonia nitrogen and organic nitrogen. It's important to know what your organic nitrogen is. Lagoons, it's harder to directly treat for organic nitrogen. Lagoons, because the organic nitrogen can sit in the lagoon for a while, sometimes the organic nitrogen will get hydrolyzed and turn into ammonia. But ultimately, there's always going to be a component of an effluent stream that's organic nitrogen that's basically impossible to treat for in a lagoon system. So it is important to know. So if you're a typical standard municipal lagoon, you typically would see about 3 to 4 milligrams per liter of organic nitrogen on your effluent, maybe even 5 or 6. If you have an industry coming in, your organic nitrogen might be a lot higher. And the way you figure it out is you go to the lab, you take your sample and you say, please give me a TKN number and an ammonia number for this. And they will do their testing and they will give you TKN and ammonia. And then you take the TKN number and you minus out the ammonia, and what is left is organic nitrogen. So it's quite an important metric to keep an eye on. The last sort of nomenclature around and category of total nitrogen is total inorganic nitrogen, which is the combination between ammonia nitrogen, nitrite, and nitrate. And so for some of the states that we're seeing, including here in Colorado, where we're based, instead of asking us a lagoon to meet a total nitrogen limit, they're saying you need to meet a total inorganic nitrogen limit. Which I think is good because, again, like I mentioned, it's hard for a lagoon to treat organic nitrogen directly. It will indirectly do it throughout the process and hydrolyze some of that organic nitrogen into ammonia, but ultimately there's still always going to be some organic nitrogen, and it's not something that lagoon operators can really control. So I always like it, hey, if you're going to give a limit to somebody, at least give them a limit for something they can control. Like total inorganic nitrogen versus just total nitrogen, which has that organic component in it that you can't control. So with recirculation, the promise here is that you can accomplish total nitrogen removal. And the way you got to do that is, with a municipal lagoon, most of your nitrogen coming in is ammonia. The vast majority of it is. And so the first thing you got to do is you got to convert that ammonia first into nitrite, then into nitrate. And you do that by growing nitrifiers. Now we have an entire webinar on nitrification, which you can look up on our Lagoon University website. I won't go into too much more detail other than the process is that. Then once you get into that nitrate form, you can convert it from nitrate to nitrogen gas. And really cool process, right? You're literally taking the nitrate out of the water and it just off gases into the atmosphere and it's gone. Really cool. So why would you want to denitrify? Now, the obvious reason is you've got a total nitrogen limit or a total inorganic nitrogen limit. Then you got to meet a limit, so you got to denitrify. That's fine. But I would argue that there are benefits to denitrifying even if you don't have a limit. And here are the two primary ones that I see. First of all, for every 1 milligram per liter of nitrate denitrify, you get 3.57 milligrams per liter of alkalinity that is produced. And so this is cool. It's a cool feature. It just gets produced, gets put in the water. Why? Why do you care about that? So what? Well, alkalinity is great for keeping a stable pH in your lagoon, and having a stable pH and having a pH around neutral keeps the bugs happy. And it's always a good idea to keep your bugs happy. The happier your bugs are, the better job they're going to do at removing nitrifying or removing BOD or whatever the things that they need to do that you want them to do in the lagoon are. So nothing wrong with having more alkalinity than you might otherwise potentially need. If you are nitrifying, then having more alkalinity is also a really good thing, because you need alkalinity to nitrify. It gets consumed as part of the nitrification process. The second big benefit is that for every 1 milligram per liter of nitrate denitrified, you get 2.5 milligrams per liter of BOD removed at the same time. And that's because the denitrification process needs to use that BOD as a carbon source. Now, I think this is awesome, right? This goes back to why recirculation helps you to reduce BOD, is because not only, as I talked to in previous slides, are you recirculating BOD back to the front of the lagoon system, where you've got this vibrant microbial community that's chomping down BOD that can then chomp down that BOD, but you also get it BOD removal from denitrifying. And that's also awesome. And the cool thing about this denitrification BOD removal is it's a lot cheaper than aerobic BOD removal. If you're doing aerobic removal, you're putting a lot of air in the lagoon, and that air costs money, whether it's a blower, a surface aerator, or whatever. If you're just recirculating, you could, for your lagoon, depending on the flows, it could be a 1 horsepower pump, it could be a 0.5 horsepower pump with basically 0 head on it. It doesn't use that much power. It can plug into a 120 volt socket. Super easy to install, super easy to do, super cheap to run a small pump like that, and you get 2.5 milligrams per liter of BOD removed for every 1 milligram per liter of nitrate. So I like to say it's free. Technically, it's not free because you have to pay for the pump recirculation, but man, it is cheap. About the cheapest BOD removal I think you can get at a fast enough pace. If you want to do anaerobic digestion, that's free, except it's very, very slow. So 2 really good reasons to do this, even if you don't have a limit. So the rub is that, like I said, because your most of your organic, sorry, your nitrogen, your total nitrogen coming in is from ammonia, you have to nitrify it to make nitrates, to convert it into nitrates before you can denitrify it. So what do you need to nitrify? Well, you need low BOD, you need alkalinity, you need ammonia, and you need high DO, okay? Now, the problem with this is that a lot of the things you need to denitrify are the opposite of what you need to nitrify. So if you're trying to denitrify, you need nitrates, right? So you gotta get rid of the ammonia and turn it into nitrates. You need low DO. You want under 0.5 milligrams per liter of oxygen, dissolved oxygen, or lower. And you want BOD because you need that for a carbon source. So it is the quintessential chicken and egg situation, because in order to denitrify, you have to nitrify first, but in order to denitrify, you need a lot of the opposite conditions you need to nitrify. So this is where recirculation comes in, okay? This is our process. This is the way we approach it. You could simply do it a lot simpler than this, but I'm going to explain our process and why we do it the way we do it. So in our process, we start with this BOD treatment in these aerated lagoons. Then we run it through our nitrox ammonia removal process, which will basically nitrify any water at pretty much any temperature, especially within a municipal system. Unless the only caveat I have is the water can't be an ice cube. But other than that, it'll nitrify it, create those nitrates, and then we pump that water back, blend it with the influent water coming in from the collection system, and then put that into an anoxic lagoon right at the front of the process. So modeling. So there isn't a specific biological model available for this type of denitrification. We are actually trying to develop that by doing piloting and gathering more data so we can get more predictability about it. But off the bat, we sat down and we said, okay, let's just think about this for a second, just theoretically make some assumptions and see where we go. So this shows you what the effluent total inorganic nitrogen would be based on recirculation rates and a assumed percentage of removal of nitrates within the anoxic zone of the lagoon itself. So we assume 25% removal, 50% removal, 75% removal, 100% removal. And I think the takeaway here is that the more you recirculate, the lower the effluent TIN will be, regardless of what removal rate you can get in the lagoon. Now, in reality, I can say today that we probably get 90 to 95% nitrate removal within a pre-anoxic lagoon. So really, really high rates of removal. But you do want to recirculate more. And it makes sense because in order to get rid of nitrates, you actually have to take the nitrates and put them somewhere where they can where they can degrade, and that's in that pre-anoxic lagoon. So the more of those nitrates you put back in the front, the more they're going to degrade. Totally makes a lot of sense. The second piece of this is that if you had, there's limitations because you always got new water coming in for total nitrogen, right? And you're recirculating water and you're getting rid of the nitrates, but you're always blending the two streams. And so do you think about it from the perspective of just use round numbers, and nobody has 100 milligrams per liter of total nitrogen coming in, or at least not in municipal systems don't have it. But say you did, right? It's usually 30 milligrams per liter of total nitrogen, by the way, or 30 to 40. But say it's 100 just because it's easier. If I recirculate 1Q, so 100% of your flow back to the front, and I get 100% removal, and I'm blending that water together, I'm only going to see about 50% of my water have total nitrogen in it at that point, right? So because I'm still bringing in that 50 milligrams per liter from the influent, and I'm still denitrifying 50 milligrams per liter from the recirc. So sometimes in theory you have to go around 3 or 4 times in terms of recycle in order to get it down low enough. But in reality, what we see is that the lagoon actually removes some of that total nitrogen in different ways and functions that aren't denitrification. Okay, so blending. Why would you want to blend your recycled water with your influent water? And why do we think this is important? Now, and you don't have to. You can just recycle back to the front. Totally your call. But with blending, I think what's really cool about it is that you are taking that high DO water from the reactor and you are mixing it with the influent water that has low DO and high DOD. And so what you do is you get all this mixing in the pipe, the DO gets depressed, and then by the time it gets put into the pre-anoxic lagoon, right here at the front, you've already got the water kind of primed and ready to denitrify within the pre-anoxic lagoon itself. And so why the picture here? Well, I got this idea to blend from this particular project, and it was a industry that was making nitrates and nitrites and ammonia for basically making TNT. They were a bomb maker. Austin Powder was the company. And they had a spill, and they had a bunch of water that had a lot of ammonia in it sitting in the lagoon, and they had to treat the ammonia because they couldn't discharge it the way it was. So we came in and said, okay, we can do this for you. So we rented them these 2 frac tanks. We retrofitted the one on the left, made it into a nitrification reactor, much like our nitrox system. Has media in it, aeration, really good conditions for nitrification. And then we flowed from there into the denitrification reactor, which also had media in it, but no air. And then we were feeding Micro C, who now EOSI, who sells Micro C, is now a partner company of ours. if you need a micro-C or any kind of carbon source. It's essentially liquid BOD is basically what it is, and it provides the bugs with a carbon source and helps to depress DO within the tank. Now, the problem we ran into with this is that we just could not get the DOs down in this tank, in the second tank on the right, because we were coming out of the first tank, really high DO, 6, 7, coming out of nitrification, bugs were loving it, and love that DO when they're nitrifying. And we go into the pre-anoxic tank, and we were fighting this DO. We could not get it down. We need to get it down below 0.5. So the classic chicken and egg I was talking about, right? Doing nitrification immediately after denitrification, doing denitrification immediately after nitrification is just tough. But so we were basically coming out of this. We're going into the denitrification reactor one, sitting there. Let's say it was coming in at 30 milligrams per liter nitrates. It was going out at like 28. Like we were getting Zippo for denitrification in there. However, it was flowing out of the back of that tank. It was flowing 500 feet in a pipe to a lagoon. And we were like, hey, let's pull a sample there. So we pull a sample there, and lo and behold, we're getting like 5 milligrams per liter of nitrates out of this thing. So somehow we were growing the bugs in the reactor. The BOD was flowing through from the carbon source. It was mixing in the pipe, and it was denitrifying in the pipe, which was crazy. And that always stuck with me over the years. I'm like, this is just cool. I don't know why this is happening. It's kind of crazy. It kind of makes sense to me. So when we came to develop our own process for recirculation, we got to blend. We got to blend because this is really going to help out. And you'll see in this pilot that we did that it's been very successful. So why an anoxic zone? So you don't have to have an anoxic zone. If you have a partial mix aerated lagoon system, you can just recirculate back to the front, and assuming you don't have too much density of aeration, you're very likely to be okay, and you will get denitrification in that lagoon, partial mix aerated lagoon, depending on how big it is and how long the retention times are. However, we like a pre-anoxic zone. One of the reasons is in a pre-anoxic zone, we know we're going to have pretty low dissolved oxygen. So this was a plant we worked on. This is one I did a sludge survey on and a DO profile on. These blue boxes on the left here show you different DOs at different depths. And you can see in this pre-anoxic zone, we are regularly seeing under 0.5 milligrams per liter of dissolved oxygen in the lagoon, which means that we can really get really fast and incredible denitrification within the lagoon. The second piece of it is that when you have a pre-anoxic zone, it can kind of act like a sludge sink, and it can allow a little bit of pre-treatment of solids that can sink to the bottom. It can also allow some of the rags and some of the stuff you don't want to get into your aeration system to sink and settle, because rags will clog up any aeration system known to man. I don't care what kind of aeration you have, rags will ruin your day. And so when you can settle it here at the front, you're less worried about rags. When you have a lot of sludge in a very concentrated location, which is slightly easier to remove than taking your whole lagoon offline, taking all the aeration out, in this case, and cleaning the whole basin bottom, right? At least with the sludge being in one spot, right at the pre-anoxic lagoon, easier to get at. And then finally, that sludge is full of BOD, right? It's a settled BOD. And as the water's coming into the lagoon, being blended and then coming into the lagoon, it bubbles up through that sludge. And that is really good. It's good for a carbon source, good for low DO, and it's good for the bugs. The bugs are living in that sludge, and they're breaking that stuff down in the sludge. So we do like a pre-anoxic lagoon when it's possible. So mixing. So I kind of seen this meme. This might be a little dated now, but this guy who likes to put up a sign, put a controversial statement on it, and then say, change my mind, and sit out in public and have people walk up to him and talk to him about, why this controversial statement is wrong. And so I always find that kind of funny because, if you look it up on YouTube, you'll find some interesting videos. But I've always thought, my 16 years of doing this, mixing is the solution to 90% of lagoon problems. And the reason for that is that, fundamentally, to treat wastewater, you're trying to get the bugs, the food, and if you're aerating, the oxygen together. And the better job you do that, the faster treatment you get, the happier the bugs are, the more microbes you grow, et cetera, right? And so in the same way with the pre-anoxic zone, if you're able to put a little bit of mixing in there, you can get the bugs and the food together, you're going to get better treatment, and you're going to get better treatment kinetics. And I can prove this to you here in a couple of different slides because we actually have some data on it. So typically we would do that, and this is like my, I apologize for this. This is absolutely dated. It's my hack Lagoon mixer job. We were pumping water through that to kind of spray out these nozzles, and it was a bit of a joke. Rev 1, just testing, not what we sell today. But we do have a more developed and better system. But this is the type of thing where you can drop it in the bottom of the lagoon. It can either spray water or burp air to create a little bit of mixing for a short period of time, and then stop, and can really make a big difference in treatment. Now, if you don't want to have a pre-anoxic zone, or you can't, or whatever, and you have aeration, you can simply cycle aeration. So this is an idea that was stolen from, or I would say stolen, borrowed from activated slugs. They do the same thing where they're cycling air on and off. Like if you think of an SBR does that exact thing, right? And so you can do that by simply putting a valve. And in our case, we have this header connected to a blower. You have these manifold points along the blower. Each manifold for our system has a dedicated valve for each aerator and air line going out to each aerator. And what you can do is you can just, isolate the manifold by putting an electric actuated valve on a timer. And if you have a surface aerator, just put it on a timer. And if you just cycle it, let's say an hour on, an hour off, or 3 hours off, 3 hours on, whatever the cycling you find that works the best, you can get the aerobic treatment you need, and you can get the anoxic treatment you need without having to have a separate anoxic basin. Finally, one thing to consider if you're trying to get denitrification is to think about covering the lagoon. Now, you saw from that previous DO profile I showed you that they were getting pretty good anoxic DO under 0.5 throughout most of the lagoon, but that lagoon is 10 feet deep. Now, for a lot of lagoon systems that are facultative, they're only 5 or 6 feet deep. And one of the reasons for that is that they are trying to rely on wind blowing across the surface, mixing the water a little bit, and creating that oxygen transfer at the surface. Now, that's great if you're trying to get aerobic treatment, but if you're trying to get an anoxic treatment, you're not going to have much of a water column in order to create an anoxic zone for denitrification. So what you may have to do is actually cover the lagoon in order to prevent that air-water contact, and therefore get the anoxic DO that you might want. Now, I would think, on a big facultative lagoon, chances are recirculation without a cover will probably be fine. But it really depends on your sludge levels, depends on how much algae you got growing in that lagoon, and so on. And a cover can really help to, let's say you created a baffled zone at the front with 3 or 4 days of retention with a cover on it. You're going to limit algae growth, you're going to limit surface oxygen transfer, and you're going to be able to create anoxic conditions. So we partner with a company that creates these hex tiles. You dump them in, they kind of nest against each other and create a really nice, tight cover on top of the lagoon, very easy to install and fairly inexpensive as covers go. So something to consider. The covers can really help. And I think shallower lagoons is really where these things are going to be worth it. Deeper lagoons, less so, because you tend to get pretty good dissolved oxygen conditions in anything under 10 feet or under. So a case study. So I mentioned this facility prior. This is up in the Rocky Mountains. This lagoon system, about 3 hours away from our office, is getting a total inorganic nitrogen limit. They have one right now of 13. It will later go down to 10 milligrams per liter. And so if you're a lagoon system and you get a limit like that, what do you do? You know, you certainly could replace your plant with a mechanical plant, but it's very expensive, much more operator intensive than a lagoon system is. And so the thought came up, like, why don't we recirculate? So this is the initial setup they have. They had a Lagoon 1 is their anoxic lagoon. They actually had one, which is cool. Then it goes into Lagoon 2, which then has 3 aerated zones, then into nitrification, and then into polishing, and then into effluent. So what we did was we looked at this and said, okay, well, if we're going to implement recirculation and we're going to try and hit their total nitrogen or total inorganic nitrogen limits, how are we going to approach this? And we started to start layering in the different phases and getting more and more intense as needed to hit their limit. So first thing to do is to recirculate back to the front and blend it with the influent water, blend the recycle with the influent water. Then second phase was adding mixing to the anoxic zone. Third phase was potentially covering it. Fourth phase was potentially cycling the air within the aeration basin to kind of essentially extend the anoxic zone into Lagoon 2. We didn't actually have to do phases 3 and 4. We did phases 1 and 2, and we're able to get the numbers we needed. So this is what we implemented. We took water out of the back of the nitrification reactor, recycled it back to the influent, blended that water with the influent water coming in an existing pipe that flew from the influent point A to the anoxic cell point B, and then through the rest of the system as normal. And so we set up these sampling points. Point B would be the effluent to the nitrification reactor, A, the influent prior to blending, C, the post-anoxic cell, and E, the effluent. And we got lab samples, and we set up composite samplers, and we also got process control sampling with the DR900 and so on. So this is the pilot we set up, and we worked with CDPHE, the regulator here in Colorado, to get this set up and to collect data and so on. First thing we did was we looked at the sludge. Again, me out and about, setting up a grid, measuring the top of the sludge blanket, taking core samples, trying to understand how much sludge they had in the lagoon. At the same time, we did DO profiling. What DO and temperature is at different intervals within the water column in 2-foot increments. And this lagoon is approximately 16 feet deep. And what we found with the DO profiling is that the anoxic lagoon was really, really good. It was very low in dissolved oxygen, which is what we were looking for. So we set it up. We put 3 pumps in there, effluent to the MBBR. These were just simple, again, low horsepower. If you're recirculating, you basically have very little lift. So basically no head on these pumps. And so you don't need big pumps. You know, these are half horsepower pumps. And we put 4 in because we wanted to be able to have 2 running or 1 running or 4 running to try and change the recirculated flow for testing purposes. Obviously, this is set up as temporary for the minute. All that water comes in, gets wide in together from the 4 pumps, then flows through the blue fire hose there, all the way up to the front of the lagoon. The blue line on the left there is simply an emergency bypass if we need to at some point, but it is not generally in operation. So a couple things we put in. We put a flow meter here to measure the recirculated flow, and then we heat traced and insulated the splitter valve there so that it wouldn't freeze on us and cause us to have a pipe burst. And we didn't have any issues. So despite the cold temperatures up in the Rocky Mountains, it can get super cold at night sometimes. It seemed to hold up at least this winter that we did it. That is the influent building on the left there. All the water comes in there. The influent, the recirculation flow meter readout there, 94 GPM, which is right around 1 Q, so 100% of the day the influent flow. And everything came in, and the recirculated water was actually fed directly behind the existing bar screen into the pipe that blends with the influent water and back to the front of the lagoon. So how'd it go? Well, They were doing some recirculation before we started, and they had 1.5 horsepower pump that was pumping from the back of the MBBR directly into their pre-anoxic lagoon. And so the first thing we're like, it's like, we gotta put this back to the front and blend it. So we put our recirculation system in, turned it on, it goes all the way to the front. And that's when we started seeing a pretty big drop off. So as soon as we started recirculating to the front, we started to see data that was a lot lower. And then what happened, and I'll show you in the next slide, is that as we got into fall, the temperature started to decrease in the lagoons because it got colder outside. And we started to see a drop off going into January and February. And so we got to the beginning of February, we got a month's worth of data from January, and we're kicking around the office. We're like, man, this is hitting the 13, like the limit, but we really think this could be better. How do we do this better? And so we actually installed mixing in the anoxic lagoon. And as soon as we installed mixing, the numbers started to go downhill from there. So it's very clear that mixing made a big impact in that pre-anoxic lagoon in terms of getting the total nitrogen, the effluent total inorganic nitrogen to go lower, despite what the temperatures are. So this is the same graph, just showing you the temperature drop. Obviously, as the temperature was dropping, we did anticipate and did see the bugs start to get a little bit strained and not be able to do as much removal. And then we put the mixer in, and then boom, the bugs started to get more access to that food and do a better job. And despite the temperatures being really low, we kept seeing a precipitous decrease in the amount of total inorganic nitrogen coming out of the plant. So very, very clearly there, we can do this in very cold temperatures. The lowest observed temp we had was 2.6 degrees C in water, and denitrification was still really working very well when we had mixing in the basin. So this kind of shows you, I like this slide a lot because it kind of gives you a visual of total inorganic nitrogen, or total nitrogen in this case, right? So again, as I said before, as it comes in, a lot of your total nitrogen is ammonia. In the case of Oak Creek, which seemed kind of unusual to us, they had like 10 milligrams per liter of organic nitrogen in their influent, which seemed kind of high, but it can happen. And only a little bit of that total nitrogen coming into the lagoon was NOx, or nitrate and nitrite. Then you go through the post-anoxic, you go through an anoxic lagoon, all of a sudden you've dropped a whole bunch of that organic nitrogen. You've dropped a whole bunch of that nitrate because you're recirculating back to the front. So you're seeing this precipitous drop in total nitrogen, which is awesome. But you still have, you've really reduced your NOx, or you've reduced a lot of the total nitrogen, which a lot of that's from denitrification. But you still have that because you haven't gone through your nitrification reactor. Then you go from there into the nitrification reactor, and now all of your ammonia is gone, right? Which makes sense. That's the nitrification reactor supposed to do. It's supposed to take that ammonia and convert it to nitrate. And so you saw a little bit of a drop there, and then you're recirculating, and then it's going through the polishing pond and out. And what was interesting about this case is a couple things are interesting that I'll dig into in a couple slides here, but right off the bat, you can see that we're recirculating water from the back of the reactor to the pre-anoxic lagoon, or to the influent that goes into the pre-anoxic lagoon. And, we have basically zero ammonia coming out of that reactor. When we get to the effluent, we're seeing this spike in ammonia. And so it's really a big question of what is going on here. Why are we seeing ammonia rebound essentially in the polishing lagoon? And there are a couple of reasons for that, and it's unusual, and it really shouldn't be happening. And this is something we want to fix when we go to put in a full-scale system. But it really is not something that should be happening, and it's skewing the numbers a little bit. So there's room for improvement here, but we're certainly meeting limits at the effluent for TIN. Recirculation, so we started off really high at about 350% of their total daily flow, and then as we brought it down and down, I think that helped the numbers a little bit in terms of 1Q seemed to be, we're hovering around 100%, maybe 90, or so recirculation rate. So average is about 119%. I think 100% is what we feel for this lagoon, what the optimum recirculation rate is. In terms of total nitrogen removal, we got about 40% across the system. Again, the cool thing about recirculation is you tend to get very stable loading on the effluent, right? Because you've got a lot of this blending that's going on, you got a lot of lagoon that's equalizing, but your influent total nitrogen is going to spike around based on INI and different factors that are going on. But overall, we saw about 40% pounds per day removed from the recirculation system. So certainly making a dent in the total nitrogen. So this is where it goes back to what's going on with this ammonia situation in this lagoon. And again, this is something I think we can fix with a full-scale implementation. But you can see here that the reactor, the red line there, was showing basically zero ammonia or very low ammonia coming out, maybe 1 milligram per liter or 0.5 milligram per liter in the wintertime. But yet the effluent ammonia was really high. So it's like, why is that happening? I mean, yes, we're recirculating, but once it gets through the reactor and it flows into the polishing pond, it shouldn't have any more ammonia in it. So why is this happening here? The second thing you'll notice here, of the total inorganic nitrogen that we're seeing coming out, a big piece of that, more than it should be, is the ammonia nitrogen. And it shouldn't be there. It should just, this is why we think we even got better room for improvement where we can hit under 10 total inorganic nitrogen on a regular basis if we can get rid of this ammonia. So what we found is a couple things. There's basically some inadvertent bypass going on within this system. First of all, Lagoon 1 can overflow into Lagoon 2 if they get a really high rain event. Can overflow into Lagoon, the final polishing lagoon. So that's the source of ammonia. Secondly, there's another form of bypass where Lagoon 2 can bypass the reactor into Lagoon 3. So these are some of the things that we're going to fix, and we actually already fixed the bypass in 2 to 3 already. But it's just a function of the lagoon design, and that's really skewing the numbers. So if we get rid of that ammonia, we really ought to be able to hit under 10 TIN consistently. And that is the plan going forward once we can remove those bypass sources. Okay, so last case study, and then we'll open up for questions. So this is in Mission Hills, California. This is one of our customers. They actually had a pre-anoxic lagoon and recirculation, and we helped them put it in. I'm going to go into too much detail on the anoxic side, but what I do want to show you is how they were able to, again, if you look at BOD here, they're really able to get their BODs really, really down, and their average ammonia down, their average TN really, really down by simply recirculating from the back of the plant to the front. And so, this is a really cost-effective way to improve your overall treatment, very inexpensive. It can help lower BOD, improve DO, reduce algae, and lower total nitrogen and ammonia. And we believe an anoxic cell is really a really efficient way to get rid of a lot of nitrates really quickly, which really can help in the overall process. Which then, again, when we get rid of nitrates through nitrification, we increase alkalinity and we reduce BOD. So that's all really, really helpful. And overall, we recommend about a 1Q average daily recycle flow. I have another class tomorrow, if you're around, on lagoon pests, where I'll be talking about that. That's the next step in the masterclass, if you're interested. All of these classes end up on our Lagoon University site. If you're not familiar with it, you can go in and get on-demand CUs and PDH credits. Please check it out anytime you want. If you need extra credits, we do it completely for free. We just want to make the information available and help you all out. So with that, any questions?
Hey, Patrick, I've got one.
Okay.
How do you mix in the anoxic zone? What are you using for mixing?
So a couple of different approaches. At one point, because I wanted to do something quick and dirty, again, hack job, not professional, but hey, I got a 5-gallon bucket. I put a 1/2 horsepower pump in the bucket. I put a hose on the end of that pump, and I drop the pump in one side of the lagoon, and then I put the hose discharge on another side of the lagoon, and in order to try to create like a circulating effect. And that worked actually pretty well. And so all the water does is gets pumped from one side of the lagoon to the other side of the lagoon. So that's a quick and dirty. The other way we've been doing it, we switched up to using basically modifying one of our Aries units, putting duckbills on it, so it's like a really big bubble, and then bursting air through that on a timer. And as long as you don't burst it for too long, you don't really add any dissolved oxygen, and you still get good mixing, and you can control the intervals of that and play with it and stuff. And right now, I think it's on 10 minutes every hour, and it seems to work really well for just creating enough mixing in that lagoon. So both of those are pretty inexpensive and easy ways to get the mixing you need.
Next one, is there any benefit to keeping a lagoon cell calm to encourage algae for phosphorus removal?
Well, the problem is that, the algae will assimilate the phosphorus into its cell wall, but if you get any of that algae in your effluent bottle, your effluent sampling bottle, it's that phosphorus is still there. So that algae, it'll assimilate into the cell wall, but if it finds its way into your test bottle, it's still going to show up as phosphorus because the phosphorus has not been removed. It's just been assimilated into the cell wall of the algae. So it's no, depending. If you can draw the water without getting algae in it, sure, maybe you get some benefit there. But in reality, it's still going to be there.
Are there any effects on pH from recirculation?
Like I said, if you are able to get denitrification, you're able to increase alkalinity. That stabilizes the pH, which is actually a good thing. Other than that, there's really no negative effect of pH.
Would recirculation work in an industrial facility where the flows and loadings might vary tremendously? Does it necessarily need to be consistent?
No, I think it almost works just as well in that context because, again, if you get extra BOD one day and it's being recirculated, you're giving it a second bite of the apple at the front of the lagoon, which is ultimately going to drive down BOD.
Are there any temperature effects to the amount of water that you would recirculate? Would you recirculate less or more in the winter?
Yeah, so if you're pulling water from the back, for example, the water will be colder back there versus at the front. Depending on what you're trying to do, lagoons, if you're trying to nitrify, the colder water is not great for you because, it will make the overall water a little bit colder because you're pulling cold water from the back and putting it towards the front. However, a lagoon isn't really going to nitrify in the wintertime in really cold water anyway. Unless you have a nitrification reactor like our nitrox system that's specifically designed to do it, you're kind of toast either way. The BOD consuming bacteria theoretically slow down a little bit when it's colder and the water's colder, but the drop in BOD removal is not enough to make it not worth it, right? Because again, when you're taking that BOD from the back of the plant where there's less microbial community to break it down, and you're putting it back to the front of the plant where there's more microbial community to break it down, the benefit of that versus the say slightly less BOD removal from temperature decrease is way higher, right? Like you're way better off recirculating because you're not as worried about the temperature because the temperature doesn't matter as much for the BOD consuming bacteria.
We'll make this the last question. What if you recirculate from lagoons 2, 3, and 4? I'm sorry, back to the front.
Yeah, I think you can do it from any lagoons that you want. It really depends on what you're trying to do. You know, I've had a customer that we had that was pulling from the back and putting in this Lagoon 2 because he felt like his Lagoon 2 needed more DO. And, you know, maybe he was trying to promote nitrification in the summertime and felt like that was going to happen in Lagoon 2. So the more DO would help. So really you can move it wherever you want, depending on how, you know, what you want to accomplish. I think the default is really from the back to the front.
All right, that'll be the last question.
Okay, well, thanks everyone for coming. We will get back to you. We're going to send out a survey after this. We really appreciate if you can give us your responses on that. That's really helpful for us to kind of see how we're doing here. Eve will be in touch with any CU PDH credits, or you can reach out. And if you guys ever have a lagoon that you're working on that you want some help with, we would be more than happy to help. This is my contact information here, patrick@lagoons.com, or my cell number here. Give me a call anytime, and we'll definitely, if I can't help you, I'll get you in touch with somebody at Chocolate who can, which we have plenty of people who can do that. So thank you very much, and we'll see you next time.